Welcome, everyone. Welcome to everyone to our Science Thursday with Brookhaven Lab. I am Aleida Perez from the Office of Educational Program here at BNL, and I'm joined by my colleague Diana Murphy, who will be managing the Q&A portion of this discussion. Just before I introduce today's guest, I have a few reminders for you. You can submit your questions by using the Q&A chat section. The chat section is on your right side of your window, and we will try to get as many questions as we can today. If you have any difficulties with the video stream, you can let IT know by making a comment in the chat section, and they will be able to help you as well. So today I have the pleasure to be joined by Drs. Vanessa Sander and Jasmine Hatcher-Lamar. They're radiochemists at the Brookhaven National Lab Medical Isotope Research and Production Program. As you know, as probably some of you may not be aware, Brookhaven has a rich history in radioisotope research. And so we are very, very glad to have Vanessa and Jasmine here today. Something that we will talk about later on as we have this discussion. I just want to point out that Vanessa is the first African-American woman to earn a PhD in radiochemistry. Congrats, Vanessa. So welcome, Vanessa and Jasmine. How are you today?
I'm doing very well. How are you, Aleida?
Oh, I'm doing well. Vanessa, how are you?
I'm good. How are you doing today, Aleida?
Oh, great. It's a pleasure having you both here today. And I know that both I know that you work collaborative together in the radioisotope group. And I know your work complement each other. At the same time, there are some uniqueness into the type of research that you do. And that's why we are going to hope to have a discussion about it today. So we are joined by a number of students and teachers as well. So before we move forward, for those of us that may not be aware, what is a radioisotope? When we think about radiochemistry, what is a radioisotope?
Well, I mean, simply put, it is a radioactive element on the periodic table. It's an unstable chemical element that, as it tries to reach stability, it emits or releases radiation.
Mm-hmm. And so that material, that chemical, then we use that to do certain application tools with it, like what we be discussing when it comes to imaging.
Exactly. So they're used, the release of this energy is used in a vast different applications. We use it for medical applications, but it's also used for energy, it's used for forensics, it's used for a plethora of things.
Very wonderful. So we're going to focus today on the medical applications of it. And I'm going to start with Jasmine. And Jasmine, I know that you've been a BNL for some time, and you started as an undergraduate student in here at BNL. Can you tell us a little bit about now, what is your current work at BNL? So your current area of research?
So I'm a postdoc in the Medical Isotope Research and Production Program. My current area of research is generating a radioisotope called actinium-225 from small targets using a cyclotron. So we have a bunch of accelerators at Brookhaven, and one of our smaller accelerators called a cyclotron, which moves things in this like a tiny circle, like the Rick, but really small. That we can use to make a very important isotope. So my project is to make targets for that isotope.
And when you mean targets, what does that mean?
So very much like the common uses of the term target, right? Like you have, like you're at an archery range, you've had an archery range or something, you have that bullseye and you're going to hit it with something. In our case, we're hitting it with high energy protons. But you can do it with neutrons, you can do it with some photons. That's the idea. Like you make a target and you put it in the way, essentially, of a high energy proton beam, and you in hopes of activating your material to make your radioisotope.
And you mentioned that you're focused in actinium-225. And so you are looking into ways on increasing the targets for production of that particular radioisotope?
So we're looking into making targets that work for our particular cyclotron. There's more than one way to make actinium. Even currently is making actinium from thorium targets using the same accelerator that feeds the RIC,
Correct.
called the LINAC, right? So, but we're also looking at alternative methods using our smaller cyclotrons so we can make small batches of very pure actinium.
Very cool. I think that's just exciting.
I think
And I think it's like in a frontier of research, in a frontier. So that's actually a very exciting question. I have a question here asking, why is actinium-225 important?
I'm so glad you asked. Actinium-225 has been shown to be very effective in the treatment of metastasized prostate cancer tumors.
Mm-hmm.
And so please.
No, go ahead.
So there was a study, there's been a couple studies in Europe and in South Africa where they have men who are in end-stage cancer. Like when you see their scans, they have tumors all over their body. And from 4 rounds of actinium treatment, all their tumors disappear.
And
now, it's not 100%. It's not 100% curative. We still have to do more research, but there's a lot of progress. And it was very impressive. These images kind of went viral in our community that you can use actinium to treat prostate cancer.
So it's like a very effective, very effective treatment for isotope. How is I just thought about it now. How is usually delivered to these patients for this particular study that you mentioned?
So the actinium is coordinated to like an antibody or an antigen. Let's kind of describe it as a bus, right? So you have a bus, and the bus has a route, right? And so your bus route is going wherever it's going. What we do, and Vanessa can give you more detail on this, but what we do is take our isotope, put it on the bus, and let that bus go to where it's going. So these antigens and antibodies are already going to the cancer, and our job is to find an isotope that we can stick onto this bus that will take it to the cancer for treatment.
That's wonderful. So now that you mentioned Vanessa, so I know that you are a staff scientist at the lab. Is that correct?
Yeah, I'm currently an assistant scientist in the group.
And so what is it now that you're researching? What is your current research at the lab?
Yeah, so I work along with Jasmine. She makes our targets, and so as Jasmine mentioned, you have this puck that's a target, put it in front of a beam, and then you make your product or your isotope of interest. But the amount of isotopes that we make are small in amount in comparison to the target. So we have to separate those two things. So the majority of my research is on figuring out how to separate what we want from the target material. And then I take those isotopes and I try to attach them to the bus that Jasmine was talking about. So one of the main isotopes that I'm working with, along with actinium-225, is another isotope known as arsenic-72. And so when we hear arsenic, a lot of people are like, arsenic is real scary because it is toxic at high levels. But what we found is that this specific isotope of arsenic-72, has really good physical properties that used in conjunction with detectors can make really good pictures of tumors or disease areas. And so this arsenic in its excited state decays and emits these particles that we can detect and they create pictures. And so I work on attaching arsenic-72 to these different biomolecules such as antibodies and then evaluating them in biological systems.
That's actually very so the arsenic-72 is an imaging tool type of application that is used. There is a question here for you, Vanessa. How effective are isotopes? What are the targets that you have? So as I guess the question is asking, so when this radioisotopes are made, how effective they are in terms of either the treatment or the image or the image application that they do?
Right. So in this field, we know that isotopes are effective in the sense that you need a really small amount of material
Mm-hmm.
to image functionality of an
Mm-hmm.
area, so let me back up a step.
Mm-hmm.
So typically, if you have something wrong in your body or something is defective or if there's a growth, you usually go to the doctor, you get like a CAT scan or you get an x-ray, and those can show you defects or abnormalities that are like grown onto. It can show you like a break if you break your arm or your leg.
Mm-hmm.
But with these isotopes that we are utilizing, we're also able to attach them to molecules and we can see the functionality of an organ.
Correct.
Like one of the isotopes that we produce in our group is rubidium, and it's used to image the heart. And so when they inject it, they can see the valves in your heart and how they're working. If your parents or if you know anyone that's ever had a stress test, a cardiovascular stress test, they can see how well your valves are working. And in addition to imaging or using therapy for these really small cancers or other diseases. So it's efficient that we're able to kind of look at more things. And then we also have the belief of what's called personalized medicine, where we don't think that there's one isotope that can fix it all. So we are under the theory or the understanding that if Jasmine and I have the same exact kind of cancer, it can present differently. And so we might need a different type of medicine that kind of does the same thing. And so being able to kind of pick and choose which isotopes also increases the efficiency because we can pick the things that actually are working for us specifically. And so then it works better because it's tailored for us specifically.
Exactly. So therefore the likelihood that it would be more effective as it's being tailored increases on that way.
Exactly.
There is a question, because I know you mentioned about that you separated materials, and there's a question that is in the chat is asking, and this might be for Vanessa, perhaps and for Jasmine too. How do you separate the actinium from the bismuth decay products?
Jasmine, you want to answer that? I can, but if you want to.
I didn't hear the entire question. How do we separate the actinium from what now?
From the bismuth decay products.
The bismuth decay products. Okay, somebody was reading up. I appreciate it.
Yeah.
Very simply, actinium and bismuth are chemically different. Give me 1 second. I have. Actinium and bismuth are chemically different, right? So what we do as radiochemists is we exploit those differences to separate the actinium from the bismuth. So we can use something like a resin, which will stick to one element over the other, and use that to separate them. Kind of like the fanciest filter you can think of.
Right.
Right. So that's really what it is. Just like with the target is made of one chemical substance, and desired isotope is another chemical substance. And just by exploiting the chemical properties, we're able to separate them.
And so how do you know that how can you guarantee that you have some level of purity when you do that kind of separation?
Well, we have various analytical methods that we use. And so while it's funny because like my undergraduate degree was in like regular chemistry, like synthesis and material science. And I thought that like doing radiochemistry would be like more difficult because it's radioactive. Coincidentally, because they're radioactive, the tools that we use to determine the purity and stuff like that are really simple. We get to take advantage of their decays and use machines to determine what they are. So we use something like high purity germanium, which just picks up the gamma radiation coming off of them, and the energies are correlated to a specific element. So we have various spectroscopy techniques that we can use, and if it's hot, it's that much easier to use most of the time.
Yeah, because there's a kind of signature from one of each of those elements that you can actually, you have, it's like a fingerprint, right? It's a
Exactly.
each one of them.
It's very much like a fingerprint.
Fingerprint. Exactly. That's
Right.
actually very
So,
cool.
yeah, so it seems like it would be more difficult, but it's just like, oh, this isn't a vial, that's in a vial. Let's put it in machine and count and see what comes out. And it's so much faster than the other chemical techniques that we used when we were undergraduates, right, Vanessa?
Yes.
I guess it's better than titrations, right? Just joking.
Oh.
So much better than titration.
Exactly. So there is another question about actinium, and it's asking how it actually works. How does it kill cancer cells? So actinium, how does actinium actually work? How does it kill cancer cells?
So basically the energy that is released is used to kill the cancer cells. So actinium decays via alpha emission. So there's this helium particle that is released from the nucleus of the actinium. And I'm trying not to get too scientific, but basically that particle is emitted and it interacts with the DNA of the cancer cells. And through that interaction, it breaks the strands and it induces cell death. And so these alpha particles have a lot of energy, and then they don't really move that far because they're like big and bulky, and so they don't move very far. So if you could get actinium close to the tumor, it emits all these alpha particles, and then they're just like attacking the DNA, and then it results in the cell death. That's probably the simplest way to explain it.
Yeah, that's pretty good. What is the half-life of actinium? So the person has actinium, you deliver actinium into the patient. For how long is that actinium, I will use the word active for lack of a better word?
So the half-life of actinium is actually 10 days. But when we think about it in terms of a biological system, we are more focused on how long the bus lasts in the body, right? And so when we do this radio labeling, a lot of my job is to evaluate how stable the actinium, how stable the actinium attaches to the bus or to the antibody, right? Because we want it to last for a long time. We don't want things to fall apart. And so if we can ensure that that stability is very strong, then we can base how long it's active by the antibody, which is typically about a day or so, depending on the antibody, what's actually happening. But biologically, what happens is when you inject this antibody system, this construct into the body, it circulates, it finds where it wants to go, it localizes there, and as the body goes through its natural metabolism, it is excreted from the body. So it doesn't stay in the body. Well, we tailor them not to remain in the body long.
Correct. That's actually, yeah. So that's just a certain amount of time, the body just through the waste the body excrete waste, it comes out of it.
Exactly.
And just so the people might not know, the people might not remember, can you remind folks what half-life is? Because we may have some younger folks as students, and just want to make sure that they know when we talk about half-life of a radioisotope, what does that mean?
Go ahead, Jasmine.
Jasmine?
I was going to add something to it, but it can all work in the half-life explanation.
Yeah.
So the half-life is the amount of time that it takes for half of the radioactivity of a substance to decay. Right? So if you have a half-life of 10 days, then within 10 days, half of your activity is gone. What I was going to add to what Vanessa was saying is that we also specifically pick these isotopes that have shorter half-lives. And the reason for that is that in the event, it doesn't clear very well from the body or whatever, you're not stuck with it for a very long time.
Correct.
And the convention is 10 half-lives. So if something lives 10 days, then the maximum amount of activity that you'll have will obviously be at injection, but the max that you'll have any activity in you is 100 days. That's very deliberate. We pick short-lived isotopes for the purpose of being able to get rid of all radioactivity, whether it's via excretion or just natural decay.
That's good to know.
We have to follow up in that the amount of activity that we inject into any biological system is very low. And so when I mentioned arsenic, we know arsenic is toxic to people, but we are talking nanomolar, picomolar, very, very, very small quantities of material. And that's kind of one of the great advantages of using isotopes, is that we can use these such small amounts to get these very vivid pictures or to induce this therapeutic effect.
Yes, a small amount and a big bang for that amount. No
Exactly.
pun intended, right? It's a big payoff, big payoff in that small amount.
And just to remind everyone, table salt can kill you. A small amount of salt makes your popcorn delicious. A lot of salt will, in fact, kill you. So it all depends on the dose that you're receiving. And this work allows us to give you a few grains to cure cancer. That's what we do.
I like that analogy. There's a question on the chat that came through that said, how do you safely inject rubidium even though it is an alkali metal?
So it goes back to the concentration again, right? So it's, I believe it's injected as rubidium chloride, so it's a salt in a solution that's injected intravenously.
Okay, so it's like you said, it's just amount. It's a question of amount. Low amounts. As another question about actinium, doesn't the energy that actinium sends out also kill the healthy cells? That's a good question.
You want me to do it, or you want to do it?
Who want to do it?
I don't know. Someone's got to set it up. Someone's got to spike. Whatever you want to do.
Okay, let's start with Jasmine.
Go.
Okay. So to add to Vanessa's previous explanation about alpha emitters, so as we said, alphas are this large thing, right? They're helium ion. It's this large charged ball, right? So because of its inherent nature of being very large and being charged, it cannot travel very far. And that's actually why actinium is so powerful, because when you stick it onto a tumor, it can only travel about 5 or 8 cells deep. So that's how we avoid irradiating healthy tissue. As we also mentioned, we don't give that much radioactivity to begin with. But the whole point of actinium being effective is that, or any alpha emitter being effective, is that the emitted particle can't travel very far. How well can you just chuck a bowling ball from standing in one place? Like maybe, you can get a little distance out of it, but you can't throw it across a football field, can you?
Exactly.
That's the idea.
And then also, in addition to the actual alpha particle not traveling far, we attach the actinium to a targeting vector that has a specific localization, or we tailor it so that it has a specific place where it's going. And so that kind of also eliminates dosing or targeting non-target organs. And so like a lot of science goes into the background of this. Is like we're trying to make sure that it gets to the place where we need it to go, to avoid all the other places, to get there quickly and efficiently. And so that's kind of all the science that we do, all the different chemistry techniques that we do to make sure that it's getting to the specific tumor that we want it to get to.
Exactly. So it doesn't, so you don't treat the healthy cells. So you end up treating the tissue, the cancer.
Find the right bus going to the right place.
Exactly.
Yep. And that's actually I think there's there's a science, there is an understanding, there's an elegance into how that is done, right? It's just not the targeting. You have to pick those molecules at the surface of those cells that actually are important to allow that, that radioisotope just to bind, it's also the amount of time that it will be stable on that hatch to that cell in order to do the job that it needs to do. So there's a lot of elegance, a lot of science that has to go into making those, to decide what targets or what molecules those, isotopes will be coated with. So I thought that's very impressive. Actually, it makes me think about maybe I should have been a radiochemist in my younger days.
You still can.
No, we'll see.
This field is incredibly collaborative. We cannot do all of it.
No.
Vanessa and I are both chemists and have different jobs. So while I'm making targets and Vanessa's doing separation and coordination, someone has to figure out which antigen is going where. So in the field of radiopharmaceuticals, we need everyone. We need physicists, we need engineers, we need chemists, we need biologists. We need all of these people because every part of this requires its own area of expertise.
Yep, and that's an impressive thing. I think that's something that science is, our young scientists that are coming up have to kind of get the idea that it's a collaborative. You have to, you don't have to know it all. You can always reach out to others that know, and together come up with, together collaborate in those research questions. I have I just want to ask you a quick question, Jasmine, because I know that BNL and manufacturers, we have our own, we have the Brookhaven Linear Accelerator here. And so the linear isotope producer at BNL here. So that linear isotope, the blip runs when RIC is running, the relativistic A heavy ion colliders. Is that correct? And so
yes,
I know that you mentioned earlier that when the relativistic heavy ion collider is not running, there are other ways that you mentioned. And one of them was the cyclotron here as an alternate way to make these isotopes as they're needed. So is that something that is currently being, are we actively doing this kind of approach at BNL, or is it something that we're working towards in the future?
Coincidentally, it's something that we used to do. Not necessarily to make these isotopes, but we've had this cyclotron for a while, and it used to run for doing some of our early PET studies. So now we're recommissioning it to bring it back online to start up with our actinium projects. So it's been ours for a while, but it was down for a while, and now we're working with a brilliant scientist in our group named Do-Yeon Kim, and he's working to get it back up and running. So yes and no.
Yeah, I think it's very cool.
No, it's not running yet, but it will be once again.
I think it's very cool because it makes BNL a quite unique place in terms of the different isotopes that we can make and the tools that we have to make those products here. To make those products. I think that's actually a very cool thing. It's good to to think about the PET scanner when they did back in the days for hard stories and so forth, and to bring it back. It's actually I think it's a good thing. It's a good thing. There's a question in the chat that is asking it has to do a computer type of coding question, I guess. What software do you use in your research for documenting data and imaging? Do you help write code for your specific isotope, or you use something that others might provide that is normally used in the field?
So for like the data that we get from a PET scanner or a SPECT scanner, I do not write code. I am not an engineer or a physicist. No. Like Jasmine said, we work with people that have written code and does all that. But the data that I get from, besides the pictures, the data that I get back are in Excel, and then I manipulate and analyze the data from Excel.
Okay.
Yeah.
Cool.
Sorry. And so we don't just take targets and shove them into a beam. We also do simulations. And so there's a software called Fluka, which, forgive my ignorance, I believe is a Monte Carlo simulation program. That one that we also use to simulate what's going to happen to the target, what we're making, if it's going to heat up, the effects of shielding. So we also use programmers and coders too. The funny thing is that most of the people doing that work are also like physicists. And so if someone was like just a coder, it would really be advantageous.
But it's the simulations are a big part of it too. You're able to predict and are able to model before you go actually do the experiment. It's actually a very important approach in the way we do science as well. That's when we science as well. I know that we're getting into the 4:30. I just want to ask a something else. I pivot a little bit. So I know that the radioisotope field, it's it's like continue growing, and research is just moving forward, particularly because it's quite collaborative as well. What is the next areas of research in the field? So when you think about radioisotope and how we target and how we, not just the manufacturing piece and how we target for treatment, application for medical treatment, where is the field moving, you think? What is the next areas of research?
I think where research is shifting, a lot of research in radiopharmaceuticals is very heavily based on imaging, and I think we're moving more and more towards therapy.
Okay. Any new isotopes that are coming to mind that might be something to explore in the future?
There's always a new isotope on the horizon. Right now, actinium is our focus, but that's also been just how the lab operates, where we are working on several isotopes to try to meet the needs of the world. So right now, our focus, but arsenic is waiting in the winds. Scandium is waiting in the winds, and many others. So it changes constantly. Our job at Brookhaven is to try to stay on top of it and to continually produce isotopes for the rest of the world. And then as soon as we get very good at something, we sell it and then start on the next thing, because that's our job.
That's something that I'm glad you bring. Go ahead, Vanessa.
Oh, sorry. Yeah. So definitely therapy is where the market is going, but also one of the challenge with some of these therapeutic isotopes that are being used is that we can't really track it. We can't see the pictures like with the imaging isotopes. So another kind of area is what's known as theragnostics, which is where you have therapy and diagnostics and you put them together and we have theragnostics. And so with the hope of that is that we can use, ideally we want the same element where there's an isotope that can image and an isotope that can induce therapy on the same biological molecule, biomolecule. And so with that, we can track it track it through the body to see where it's localizing, make sure it's at the place while you're inducing therapy. We can be informed on how much therapeutic dose we should give the patient.
Yeah.
Those things. And then also you asked, what's the next big therapeutic? Well, that goes back to this personalized medicine. Like we're definitely looking for the next thing because like I said, what might be good for you might not be good for me. So we're trying to find and produce all of them so that we have a really vast library of therapeutics, alpha therapeutics, beta therapeutics, and imaging agents.
That's actually, that's right. The personalized medicine is something that I think it's across the field of different, treatment-based products. That's something that it's coming up. I like what Jasmine said about, that, we are here, we service, BNL program, radio program service to others. There's no competition. Once you develop a product, you have a method, just release it out, and then you work on the next one. In many ways, you're serving to meet the needs of the nation when it comes to this medicals and tool needs. I think it's a good. I like the way that sounds. It's a good way to say it. So we're going to pivot a little bit now, and I want to ask you, Vanessa and Jasmine, about your journey as a scientist and the path that we all take. So I'm going to start with Jasmine, and then I'm going to move with Vanessa. So Jasmine, how did this all started for you? How did you decided that I am going to be a radiochemist today, or a chemist? How did it all started for you?
I think I decided I was going to be a chemist like last week or something. When I had originally started my education journey, when I started college, I was going to be a nurse. I wasn't sure what I wanted to do with my life. I liked people enough, and I was like, I'm going to go be a nurse at community college, 2 years, you get out, and then you make money.
What happened?
I realized that I am not very good in emergency situations. First thing I learned, that someone almost fainted when we were dissecting frogs, and I was like, no, this isn't the thing. But more importantly, that's the real thing. I have to tell you that story offline, but she got dizzy and I moved. Like, it's very bad. So I'm always very sure to tell people I am not that kind of doctor. Don't tell me about your problems. But while I was at my community college, I met a professor who was going to Brookhaven National Lab to do research. And it was just the coolest thing in the world to me, like the idea of being able to create science. And it's not something that you can read in a book. It's not something that exists yet. And that was just the coolest thing in the world to me. And so I went with her to do my first summer internship from the CCI program.
CCI is a community college internship for folks that may not know.
Yes, thank you. And I had done my research there with her in the chemistry department. And it was just doing research at a professional level really kind of shaped my path as a scientist. And so, but even then, it was still like, I still didn't necessarily want to go all the way into getting a PhD. I just kind of liked research, and that was enough. But after that first summer, I just kind of stayed working in research and stayed in contact with her. My research started to grow and get more intricate and complicated. And next thing I knew, I had a bachelor's degree. Like, just because the research was so, I want to say fun. It's not, research isn't frustrating, but like, it's like such a rush when something works.
Yes.
Or you have a hypothesis about something and then it works out, and even your advisor doesn't know what's going to happen. Then you come with your data, you're like, look at this, I did that. Like, my name's on it. And it's just, so thrilling sometimes. Not that it's not frustrating, but it's just really the coolest thing I've ever done. And so it's just like, it just amazed me that it was enough to kind of pull me through some of these very challenging courses. And then after I got my bachelor's degree, I swore I was not getting a PhD in chemistry. While I enjoyed it, I didn't want to sit here and spend another, I didn't want to go to graduate school, but I also needed a job. And where did I go and work? Brookhaven. I was an intern in the chemistry department for a couple of years. So when I graduated, they were like, of course we'll take Jasmine. We trained her. So I worked as a technician in the chemistry department for a few years, and then I found a project that just made so much sense to me, where I felt like this is it for me. Right. And the project was a radiochemistry project.
And that was
doing chemistry in service of the world, immediate service of the world. And that's what got me, really. So then I went to, right.
No, go ahead. And then you went your PhD?
I went to graduate school and I got my PhD in radiochemistry. I also was like, okay, I've had enough time at Brookhaven. Probably not going to come back here. And then in the last year of graduate school, another department where they were doing radiochemistry, because I didn't even know much about the radiochemistry happening at Brookhaven. In another department, in the Merck group, they were doing radiochemistry and said that they could really use some well-trained hands. Because we learned how to use a very messy isotope that we were able to keep clean. So I wound up going to Brookhaven to finish my PhD, and then I got hired as a postdoc. So be very careful about what you say you are not going to do, because.
What I love that you say about the passion of the joy of discovering. I think that's something that it's I can relate to that, and that joy of discovering that you almost feel like you are the first person in problem. Sometimes you are the first person to see that result, and it just is thrilling. It's a thrill to see. So you are here, and I hope you stay here, Jasmine. Just saying, okay, Vanessa. So what was your path? How do you decide that this was something that you will become a radiochemist?
Yeah, similarly to Jasmine, my whole adolescence, I knew I was going to be a trauma surgeon. I aligned myself from like junior high or high school that I was going to go to college and then go to med school and become a trauma surgeon. Like, it was specific. I knew what I was going to be. And so when I went to college, I was a pre-med major, and I became so bored in my biology classes. Like, it was tough. I was just like, biology and like anatomy classes, like they were fine. It was just like not challenging. Sorry to the biologists. I love y'all. But like, I just was like missing something. And so one summer during my undergrad, I got the opportunity to join this radiochemistry cohort where we went to another college in Texas, University of Texas at Austin, and I got to work at a nuclear reactor for a summer. And we were doing some forensic type work where we were trying to detect materials that would be being transported on like a submarine under the ocean. I thought that was really cool. And then around the same, I still knew like I wanted to do something medical. And so I had also done a biochemistry internship, and I was like, okay, this is kind of cool, but bio, and I'm still a pre-med major at that point. So my advisor was like, you're good at chemistry, you should just switch to chemistry. So she got me. So I did that in my junior year, which that was a choice. And along the same time, my father actually got sick with Alzheimer's. And so at that point, I was like, man, pharmaceuticals seem really cool. It's chemistry. It's still medical because it's trying to find a cure for things. And so I was actually thinking I was going to go into pharmaceuticals. And then my advisor at the nuclear reactor was like, if you're good at this radiochemistry thing, if you like it, there's a grad school program where you can kind of do radiopharmaceuticals. And so he introduced me into one of my PhD advisors at the University of Nevada, Las Vegas. And so I went there and I worked with technecium chemistry and started doing radiopharmaceuticals. And then this is a funny story, but I was doing work in Las Vegas and I needed to do animal studies to complete my dissertation research. And so I ended up coming to New York and going to Hunter College, which is where Jasmine was for grad school. And so her advisor and my advisor, her advisor was also my co-advisor. So I finished up my research here in New York. And then after I defended, I came out to Brookhaven as a postdoc. And then I guess they liked me. So they decided to keep me. And now I'm an assistant scientist.
That's an awesome story. That's an awesome story. And then, like I said in the beginning, you are the first African-American woman to earn a PhD in radiochemist. And that is something that I think we're proud to have you here. I'm glad that you are part of the BNL community, that you are here and not other place, here. And that's something that I want to say. I know that our time is getting short. Before we leave, I just want to ask any advice that you would give to these young scientists that are listening to us today. What advice would you give them?
Vanessa, do you want to go first?
Yeah. I would say stay open, because as you can see, the things that you might not think you'll like, you'll actually really enjoy. I would say get into the lab early, try a lot of different things. You'll never know what you might like. And get a mentor from early. I mean, guessing most of you guys are somewhat involved in STEM. Get a STEM mentor. I have multiple mentors still.
That's a great advice. How about Jasmine?
I should have let her go first because she took everything I was going to say. I would actually just second that. Be open. Try anything. Stay in contact with the people that you do internships with, because what happens is that they invest in you. They care about your progress. It's not like, we make the joke that we're cheap labor as graduate students and postdocs, but the reality is these people are putting into you. So they would love to reap the benefits of furthering your career, putting you in contact with their people. And if you get the opportunity, go to conferences. Yeah. If you have anybody willing to pay for you to go to a conference, go to a conference, network, meet your friends, meet the people who are going through the same thing that you're going through, because that will also help push you through this field. As Vanessa and I mentioned, we went to graduate school together. She finished a bit before me, but we have been through quite a few things together and experienced a lot of the highs and lows that come with doing research. And you finding your tribe is one of the most important things that you can do and while you're developing your career.
That's just wonderful. I second that. It's important. Finding your tribe is important. So we are out to that 4:40. We're at in that 45-minute mark. This was fun. This went so fast. We should do it again. We should have like a second one. This was great.
Whatever you want.
It was wonderful. Thank you, everybody, for being here today. I hope you all had a great time. I think we need to do a second one. I say that already. Thank you, Jasmine. Thank you, Vanessa, for your time. We appreciate the work that you do and the insights that you share with us today. Our next Science Thursday is August 22nd, and our guest will be Luis Betancourt for the chemistry department. I would like to say thank you to Brookhaven National Lab for hosting the event today, for the Office of Educational Program, and I encourage you to check our programs, our research and industry opportunities, and available virtual contact on our website. Thank you very much and have a wonderful day.